Welcome back. That day we were talking about the active faults, and it's important. Now this we left here where we were talking about that how the elevation change because of the multiple earthquakes on the surface has been used in constructing the garden. Now this garden, the photograph which you see here is the uh, garden which was been constructed by Mughals in 17th century using the fault scarp, okay. But they were not aware of that this is the fault scarp, and if in near future the earthquake comes, this will be damaged anyways. But one thing is there that the recurrence on this fault is more than 500 years. So since the construction of this garden or the structure on the fault has not been destroyed because of there is no event after that, okay. But there is a likelihood of having an event on this in near future. So this is the fault scarp which you see, which they call big step in the Pinjore garden, or about 25 to 30 kilometers from Chandigarh, and this is one of the famous architect of in a small area which is similar to the Shalimar garden in Kashmir and all that, okay. And even you can find similar type of construction of the gardens in Delhi. Now this is what we do usually, that we mark the faults and then we try to look at that what is the length of the fault, what type of deformation which one can expect here, okay. So these are the different type of faults which we have marked. There is like thrust faults here, there is another one thrust fault here, another thrust fault here, and this one is the strike slip fault. So like in terms of the hazard, if we take just close to the this is an Indo-Gangetic plain and the Chandigarh city is located here. So close to not very far from Chandigarh, you have almost like 1, 2, 3 and 4 active faults which are sitting, and they are capable of triggering the large magnitude earthquake, because we see the paleosurface rupture. That is the ancient signatures of ancient earthquakes on the surface. So this is just to show that how far we are sitting from the well planned city of Chandigarh. So this is the fault scarp close to Chandigarh, which is around 15 meter. The lower one is around 15 meter and the higher one is more than 35 meters high, okay. So there are two fault scarps, so this again indicates that there are multiple events which occurred along this fault, okay. And this is the boundary between the Indian plate and the Eurasian plate, which marks the foreground here. This is an Indo-Gangetic plain, and this is the boundary which is between the sub-Himalayas, Shivaliks, and the Indo-Gangetic plain, and this is bounded by here what we call the Himalayan frontal thrust. So this is one of the most active fault system in Himalayas. Now again I will show a couple of, I will be little quick in this part and then we will move to the another topic of that on the dams and tunnels. But before that we will look at some field photographs where we see that the structures have been constructed on the fault, okay. Now the previous slide which I was showing, that the Pinjore garden fault which was constructed on in Pinjore garden, the structure was constructed on Pinjore garden fault here, and that was in 17th century, but this is very new in the last decade only. This has been constructed maybe 6 to 10 years back, okay, or maybe even younger structure, okay. So this, if you look at carefully, this part is the higher ground and this is the lower ground, and this area is the Western Command area, okay, Western Command Army settlement, and this structure which is their officer mess is sitting right on the fault scarp, okay. And there are several structures which we notice are sitting right on on the active fault. So, this is again without having understanding. So, people not we were not having any understanding at the in 17th century, but during the recent period also we have done the same mistakes. Okay. So, this is extremely dangerous. This photograph I took from the fault scarp looking to the Indo-Gangetic plain, and if you look at the construction which came up in Panchkula, okay, which is hardly 2 kilometers or less than that, sitting close to the Himalayan front. Okay. So, this will be most of the time this will be hazardous, okay, because this buildings usually what we experienced in 2001 Bhuj earthquake was something like this. Okay. So, you are having the open like this is the most dangerous part which I feel is that the construction which is sitting hardly few kilometers from the Himalayan front. Now, if we look at the type of constructions which we had in Ahmedabad, which is sitting almost like 350 kilometers from Bhuj, and this we experienced in 2001. Okay. So, usually most of the buildings, if you look at, what we see is that we have the open story ground floor, okay, and this can result into the problems. So, this is what usually will happen actually. So, when you are having the open story ground floor, which is mostly used for parking and all that, okay, so this will go down. So, this is extremely dangerous part in terms of the construction of the buildings and all that. Okay. Now, I will just skip this and move ahead. This is an example of the strike slip fault which we were talking about here. The this one actually is a Taksal fault. So, I will give the, I am just showing the example of that. Okay, how we see the ground deformation or the surface manifestation of the strike slip fault on the surface, and this is again hardly 25 to 30 kilometers if you take the flying crow distance from here, from that is from Chandigarh. So, we have a very prominent strike slip fault which is running over here, which goes almost for 35 to 40 kilometers, and it is well marked with the offset of streams. Okay. So, we have almost like the fault scarps which range from 12 to 30 meters high, and the vertical displacement goes up to 50 meters. I will show the example, the ground photographs of this scarp here at Taksal. So, we have stream offsets which we have mapped and measured, and then we have the, that is what it shows the strike slip motion, very much similar to what we have been talking about the San Andreas fault system. So, this part is the Taksal which I was talking about, that we have a very prominent major offset there, and which is quite old and sitting like, I will show a couple of photographs of that. So, this is the stop which if one moves from the Chandigarh to Shimla, then you crosses this location actually here by train. So, there is an offset here, the stream comes and then this is an offset here, stream flowing from this place getting offset. So, this is the fault trace here, this one. So, this right lateral offset is the part of the Taksal fault. So, the ground photograph where you can see the offset here, there is the river bank which turns here, goes here, and then goes like this. The fault runs somewhere over here. So, if you look at that again without having understanding, a lot of lifeline structures have been constructed on the top of this fault or at the on the fault scarp. So, this is an offset here, and this you can see this is on the fault scarp. So, this will go off, okay, like this will be damaged, severe damage on this and this, because they are very close to the fault scarp. So, at least we need to know that where this type of fault lines crosses, and we should avoid constructing lifeline structures. And we also noticed when we were doing the field here that even the schools have been constructed on this fault. Okay. So, the examples which I was trying to give here is that In the past also people did mistake, and in the recent times also people are doing mistakes because of the less awareness of this faults. Okay. So, this is an offset in from the ground, same photograph, which is we are looking from here. So, this is an offset here almost like 500, the offset was around 500 meter or so. Then coming to this again another very beautiful example, but very dangerous in this in terms of the lack of understanding of active faults. This fault scarp I have shown before also. So, this is what we call, we have named this as an Hajipur fault. Now, here what we see is that we have the influence of the displacement which was during different earthquakes in the past, and those displacement have influenced the landscape evolution. So, the Bias river which flows from here, Bias goes like this actually. Okay, this boundary, if you see this Bias river boundary. Okay, so Bias river used to flow across this before this fault propagated this side. Okay, but now it has been forced to shift here. So, shifting of streams and the shifting of major rivers are sometimes related to the earthquake or the deformation in the active zones. Okay. So, this part if you look at this is what we have generated the contour maps, and you can see the two very sharp elevation change here. Okay. One is here, another one is goes here, and then third one is over here. Okay. So, this sharp change in a very young deposits clearly indicate that this is because of the ongoing deformation in Himalayas. This is the satellite data which shows the U-shaped like turn of the Bias river. So, this is not because of some artificial construction, because this is naturally this has been moving, but pushed because of the development of these two faults. Okay. So, this area is higher because of, and then they got uplifted in multiple earthquakes, and this forced the this river to take a U-turn. Okay. So, there is a deflection of the channel over here. Okay. So, we again we do the paleoseismic studies to identify that how many paleo earthquakes have occurred here, or and what was the displacement, what would have been the magnitude at that time. So, that all we can try to identify with that studies. Okay. So, my only point is here what that this is an old picture before the construction of the Bias dam over here. Okay. In the upstream here there is a Bias dam, Bias reservoir, and what they did was that they took up the water from here. So, again it is one of the like very good engineering project, but with lack of understanding to us, which we consider that it is dangerous. Okay. So, they constructed a tunnel here, sorry, the canal here, and they put two hydropower stations on this one. Okay. So, one was been put on this carp over here, and another they put on this one. I am just putting in approximate, next picture we will be able to see that. Okay. So, they took the water from here, they generated electricity, hydropower station, another one from here, and then they poured the water again back to the this stream. Okay. So, they are not wasting water. So, they are utilizing this water and then passing on to the same channel. Okay. So, this is one good thing which they have done, but without having understanding that where they got the elevation change, they put they took a hydropower station. So, if you see the same photograph which you are looking at here, the close up of that. Okay. This is one. This is the recent photograph taken by the Cartosat satellite. This is a Cartosat satellite data, where you can see the tunnel. Now, sorry, the canal which has been constructed on along this bridge, and then two hydropower stations are sitting here. Okay. Now, these are exactly sitting on the fault scarp. So, if I put a line here, this is what we call the fault scarp here. Okay. So, very sharp over here, very sharp over here, and then in the frontal part. Okay, there is another fault scarp here. Okay, so without having the understanding, this was been done, and this was done not very long back, maybe hardly after 64 or 65, because this satellite data, there is a corona satellite data which was been collected by US satellite is not very old. Okay, so hardly a couple of couple of decades back they have done this. Okay. So these are the two hydropower stations which are sitting exactly on the fault scarp. These are the close up of that. Okay, so we have the fault which is running here. There is a Google picture which shows. So and then they have constructed this. Now the what hazard will have, because if the earthquake occurs, definitely there will, this area will break actually, and there will be in surface rupture. Okay. This surface rupture will damage definitely this fault, this structure on the or sitting on the fault scarp. Okay, and there will be a local flooding which will be extremely dangerous. Okay. So this is one reason that this what we did was we did GPR, ground penetrating radar, and tried to find out the near subsurface deformation. This is our fault plane actually, and this is the fault scarp here. So we open up the trench and then we date the soil to identify the events actually, and then we bracket. Okay, that this is the fault plane here. So this fault plane did not rupture this soil, but ruptured this soil. So we say that okay, fine, the event occurred between this and this actually. So that is how we have we do and try to identify the ancient earthquake signatures. Okay, so this is one example of that, and then we talk about what was the net displacement during one event, and then what is the slip rate and what is the recurrence interval. So recurrence interval is almost like 1000 years here. But our recent studies which we have done in greater detail, it shows the recurrence is a bit less, like around 800 years or so. Okay. So if we consider the last event which took place in 1500 AD, then when will be the next one? Okay. So we can expect in after 800 years on that. Okay, 500 years are almost gone on this. So we can expect an earthquake in near future. Now this is just to show the example of from Japan, where the length of the fault is extremely important. So this is a story which talks about the Shimane power plant on active fault actually. Now this is again, and you might have learned about that 2011 there was a massive damage to the Fukushima power plant, and this is another that similar type of nuclear power plant which must be maybe having the effect of the earthquake if it is triggered on the this Shinji fault. Okay, Kashima Shinji fault. Now what happened here was that when this was been constructed, okay, the fault length which was been taken was shorter. Okay, and if you have the shorter the length of the fault, you underestimate the magnitude, and that what happened. Okay, but recent studies which were been taken up by again by Professor Nakata, which shows that there are few locations where there are no manifestations clearly seen. Okay, because of the modification, or because by the anthropogenic activity, or because of the erosion which is taking place over time. So what he suggested that the fault length is not so short, and whatever the hazard which has been taken into consideration for that power plant or the risk is underestimated. So this is one of the important part which one has to look at. Okay, so that drastically, if you consider the length, lesser length, then you will have you will be underestimating the hazard on that particular region. So here I end this part, and we will start a new part which is again related to the faults and all that, and that what we call the role of geological structures in civil engineering. Okay. So this is we will see how the geological structures so are important. Okay. Now, we in the previous module part 1 we talked about different type of folds, okay, and here you will find that how important they are in terms of identifying the locations of any civil structures like dams and tunnels and roads, and how in like dangerous it would be if we fail in identifying those things. Okay. Now, folding within rocks, this is what we have talked in the previous part also, or the sedimentary succession are developed mainly due to tectonic forces or tectonic deformation. Now, this stresses result into development of strain within rocks, whereas when released by human interference. Okay. So, if we keep on doing this at a number of places. Okay. So, by excavating tunnels, again if you are having the folded, because you are putting tunnels in the mountainous areas, and mountainous areas are nothing but in Himalayas, if you take, they are the folds, they are all folded mountain chains. Okay. So, if one we are doing that, we are releasing the pressure, or what we are doing is we are putting excavating the area, huge area for the reservoir. Okay. Or we are doing minings in the area. Okay. That may result into the surface bulging at some point of time. Now, the geometrical setting, okay, geometric setting of any fold will be different. Okay. Like what we have learned is the anticline and syncline. Okay. And the fractures within the folded areas, because definitely if you fold the crust, so brittle in nature, it will fracture also. Okay. So, fracturing can also result into the caving effect, or maybe it will result into the groundwater, okay, percolating down that. Okay. So, that is, those things are important, and while laying the tunnels, it is extremely important to know that how deep is the fracture and how long it persists. Okay. So, that is the another part which we will talk in this. Okay. So, the geometric setting of different type of folds are very important from civil engineering point of view. Likewise, in selection of dam sites, tunnels, locating groundwater potential also we can do that. Okay. And laying roads and rail tracks along the hill slopes. Okay. Now, this is just a photograph which we took on from a small dam structure. Is a gravity dam on one of the tributary of Yamuna in close to Dehradun, and what we found here is that was extremely important. So, if you look at this beds here, they are dipping in the upstream direction. Okay. And this is a part of the fold which they have identified. So, of course, along with the understanding of that, whether the foundation is stronger, we have learned different type of rocks, either it is in terms of the metamorphic, igneous or sedimentary, which rock types we are able to see here is extremely important. So, once you have identified the site, the geological aspect has to be taken into consideration in depth, okay, in detail, because you see the different type of rocks there. If you are encountering shale, which is an argillaceous rock, sedimentary rocks, it's very fine and have different drawbacks. Okay. So, those type of sites should not be taken into consideration. If you are, for example, you are coming across granite, so very hard rock, okay, compared to the other igneous rocks or the sedimentary rocks, or you are coming up with the sandstone, massive sandstone, then those are good. Quartzites, again metamorphic rock is good. So, you have to be careful that what is the foundations you are coming up, and then accordingly geotechnical people can take up the studies talking that how to strengthen the foundation. But the initial geological information is extremely important before you design the dam, before you take up the project. Okay. So, this is one point here. So, let us see and how we suppose we are having an syncline. Okay. Suppose we are having a syncline and we are putting a structure on the top of that. Okay. Then what will happen? So, and we are having the reservoir in the upstream side. Okay. So, we will come up with two vectors and we will have a resultant vector here. Okay. So, one is the thrust, and this arrow shows the percolation of the water back into the reservoir. Okay. And then we are having this, what we say, the inclination of the limb, okay, will play an important role, okay, which could be result into the favorable conditions, could result into the unfavorable conditions. But W is the weight of the dam structure, which is acting almost vertically downward, and T is your thrust due to the reservoir. So, these are the force vectors for which are acting, and then a resultant of that will be your R, okay, which will be inclined to the stratus in the downstream. Okay. Now, if you are having near to perpendicular, then it is almost good to put or advisable to take up the structure there. Okay. But it depends, that inclination may vary from 10 to 13 degree in most of the cases. So, the beds which have gentle upstream dip will be perpendicular to the resultant vector, you will find this, okay, hence can provides the best resistance to withstand the stresses or the loads acting on the area. Okay. So, this is one of the ideal conditions we will have. Okay. So, if you are having syncline or the beds which are dipping in upstream direction, that can be an ideal location. Okay. Now, dam over and undisturbed again. So, this is considered to be most ideal, but sometime you find that there is a problem of percolation of the water, and that can result into some uplift pressure, but this will be minimized because of the heavy weight of the structure on the top. Okay. So, this is one could be an okay condition, like not very good one, but fine. Okay. So, that the percolating uplift pressure can be minimized, but to some extent. Now, coming to the other example, that is, suppose you are coming across an syncline or maybe an anticline within the beds dipping in the downstream direction, you will have a lot of problems there. Okay. So, if you take two vectors W and T, okay, and then you are having resultant one, which you will find this is almost inclined, okay, and this is not good. Okay. So, you will have some uplift pressure here, and then water will definitely leak down into the downstream direction. So, you will have the loss of water, and then resultant vector keep on changing here, and it will be quite inclined. Okay. So, this is not very ideal condition to be taken into consideration. Okay. So, R will be parallel or nearly parallel to the bedding planes, okay, and then looking to the downstream direction. Now, locating dam, if you look at, so we are having like the folded structure, okay, if you take into consideration the whole one, okay, and then if you put your structure here, or so then you are having very inclined. So, it is quite possible that you may face a sliding problem here, and then the water will keep on percolating down. Okay. Here it is extremely good, okay, but here it is not at all. Okay. You may have the problems. Okay. So, this is the most ideal one. Okay. Now, what problem we'll see usually? Okay, we'll come across, like if you are having the faults. Okay. So, those were the folds, and now if we are looking at the fault, mostly you will come across the shear zone. I'll continue this in the next lecture. Let us stop here. Thank you so much.